All right, here we have section 5.7, the substitution method, or much more commonly referred to as U-sub. U-substitution is one of the most powerful and general methods of integration. It's extremely powerful, and most other more sophisticated techniques of integration are at least in part based on U-sub, or they distill down to this method. So really the substitution method, or U-sub, is really, it provides a way of undoing the chain rule for differentiation. Of course, the chain rule from Calc 1 is a way of differentiating, it's a rule for differentiating a composition of two functions. So a function within a function, how do you differentiate that? So of course we know, if we take a look here at this theorem, the formal statement of U-sub, or the substitution method, here we can see that this is exactly, or at least let's say nearly what we have for the chain rule. Of course, for the chain rule, if I have a function capital F as the outside function and a derivative, and an inside function of u, if I take the derivative of this composition, the chain rule says the derivative of the outside function, leave the inside function alone, multiply by the derivative of the inside. So now this statement here says, what if we assume that capital F is an antiderivative of little f? Well, all that means, if we take this statement and translate it symbolically, this essentially means, so in other words, f prime, capital F prime, is little f. So this statement here can then just become little f of u of x, u prime of x. So really the integrand here is exactly the result of a chain rule, and then we just pull it back. Okay, so let's actually take a look in action to see how this how U-sub is used and how we can do some of these integrals. So we'll take a look at example 1, part A. We've got the integral of 3x squared e to the x cubed. First thing we want to go ahead and get used to is if your integrand contains a composition of functions. So right here, this e to the x cubed, our outside function is e to the x, our inside function is x cubed, then you may want to consider using U-substitution. So the way U-sub works is we will begin by selecting the inside function to be our u. So let u equal x cubed. Then we need to find the differential dx. So we'll take a derivative. Du is equal to 3x squared dx. Great. So now we can see that the 3x squared dx is right here, so that matches. And then the x cubed right here can become our substitution variable u. So this entire integral, you don't have to do this, but mentally it can be useful for some people to think of it as grouping the 3x squared and the dx together. So then you really have this piece here, which will get replaced with a du, and then this box around x cubed gets replaced with this u. So then you can just swap them out. So e to the, let's write that down properly, integral e to the u du. And then of course the antiderivative of e to the u is e to the u plus c. And then we go back. So u is equal to this x cubed. So e to the x cubed plus c is our antiderivative. And like always, if you want to check your answer for an integral, you can just differentiate this, and you should get back the integrand. Okay, part B, a really similar looking integral. Let's go ahead and use that same sort of technique where we're going to let u equal the inside function, since we recognize that we have a composition of two functions. Find our differential du to get 2t plus 2, that quantity, times dt. And we can notice here that the 2t plus 2 does not match what we have here, this coefficient. So what we could do is we could just say, well, let's factor out a 2. So now we kind of, or a little bit more closely, have what we need. And we really just want to get rid of this 2 so we can divide that 2. So 1/2 du is equal to what we have, t plus 1 dt. And again, you don't have to do this rearrangement, but a lot of people do this in their heads. I certainly do this in my head. If I have a complicated integral, I'll move this t plus 1 next to the dt, and then again I can say that this piece here in blue is this piece here in blue, and this piece here in red is this in red, right there. So then this becomes the integral e to the u, and then this t plus 1 dt becomes a 1/2 du. So 1/2 integral e to the u du. So this becomes 1/2 e to the u plus c, and of course we'll back substitute, so e to the, what was u? U was t squared plus 2t plus c. Okay, moving on to part D. So we can do a u substitution here. Again, identify the inside function and use that for u. So then we will have dt, du equals dt. So this integral here, I'm going to continue below instead of to the right since I don't really have much room here. This would be the integral of 1 over the square root of u. Dt becomes a du. So of course we can write this as u to the negative 1/2 du, and we can integrate this to get u to the positive 1/2 divided by 1/2, so multiply by 2, and back substitute. So 2 times the square root of t plus 12 plus c. And I realized that I went to part D instead of part C. So let's backtrack and do part C. A little out of order. So for this one, let's go ahead and let u equal the inside function. So we get a negative dx. Now notice there's no negative coefficient here, so I can divide by that negative 1 to get negative du equals dx. Now we have our matching dx, so that's good. So if we think about this, the inside here would become a u. This dx would become a negative du. But what to do with this x squared? Well, one thing we can do that we haven't yet done is we are able to manipulate this equation as well as this equation. So let's focus on this equation at u equals 1 minus x. We can go ahead and take this to solve for x, to get x equals 1 minus u, and therefore this implies, of course, that x squared is 1 minus u quantity squared. So we could replace this x squared in the integrand with this slightly more complicated looking expression, 1 minus u squared. So you might think, why would we replace something so simple as x squared with this whole quantity being squared, something that we are possibly going to have to FOIL out? Well, just because one step makes this one little component of the full problem more complicated, it does at least make the problem tractable. Whereas before, sure, it might look a little bit more compact and nice, but we don't know how to integrate it. So sometimes we sacrifice the way a problem looks. We swap that out for something a little bit more complicated looking, but at least we can solve it. So in this case, we get a negative du for this dx. So if I have a coefficient, I can always just pull that out. So that negative du, the negative I can take out. So then the x squared would become a 1 minus u quantity squared. The square root, of course, becomes square root of u, which I can, of course, write that as a u to the 1/2. Let's just do that now. And du. So I will first expand this numerator. And then we can algebraically split the fraction so that we have u to the negative 1/2 minus 2u to the positive 1/2 plus u to the 3/2 du. And integrating from there, leaving that negative all the way out in front. So I'm using the power rule a bunch of times. Let's see, we'll get a 2/5 u to the 5/2 plus c. And of course we can simplify and back substitute. So this would be negative 2. Our u is 1 minus x. So this would be 1 minus x to the 1/2 minus 4/3 1 minus x to the 3/2 plus 2/5 1 minus x to the 5/2 plus c. And there we go.